All right, let's continue our discussion of Hardy-Weinberg Equilibrium. I've drawn a little rock over here with two different types of beetles. We have some beetles with these red carapaces, and beetles with white carapaces. So let's pretend that these red beetles over here, this is a recessive trait. The trait we want to look at is this carapace color, and this one is red. So we have, and I usually do this for each of these problems, I would recommend you write something like this. Let's write allele, and let's draw, let's draw a line straight down here, as straight as we can. And let's divide that into genotypes. Genotypes. Okay, alleles. So you can use any letter you want. I think for this one, since we're dealing with something that is red, and we'll say that the recessive trait gives us the red shell, let's use the allele R. How about that? R and R. Of course, you also have to know what these Hardy-Weinberg variables are. And the Hardy-Weinberg variables for each of these that we're going to use are P and Q. So I'm just going to make this equal to P here and Q. All right. So I'll erase these little equal signs here. So this is just going to, I don't want to get us too confused here, but I'm going to put these in parentheses just so you remember that P represents the frequency of the dominant allele, and Q represents the frequency of the recessive allele. Okay, now on the other side, genotypes. What we have a simple dominant recessive system here. So what different genotypes would these give rise to? Well, you guys have probably seen this before already, but you can have big R, little r, and I'm going to put down here, I'm going to even separate it a little bit. Let's put little r, right? Of course, I'll put these in parentheses too, because we know each of these genotypes is represented by one of these Hardy-Weinberg variables here. P squared, 2pq, and we'll go way down here for q squared. Okay. Now, the reason I put a little bit, I'm going to put a little dotted line here. The reason why I separated out this, okay, sorry about that. Okay, the reason I put this little dotted line over here is to kind of show you that these two up here, they are going to give rise to a certain phenotype, right? And you can even write this out if you want to. Phenotypes. So, across this dotted line, what phenotypes are we going to get from the dominant allele up here, which is going to give rise to big R, and big R, little r. That phenotype in my little system here is going to give us a white carapace. White beetles, right? Okay, let's look at this other one over here. I've told you that this is a recessive trait. This means that it's going to give rise to the red beetle, a red carapace on these beetles. Carapace is that shell surrounding these beetles. Okay, so big R, little r. So we need to find out, in this case, what our allele frequencies are. Let's pretend that you counted these beetles. You counted them on tons of rocks. It's a huge population. Let's say that there's a total of, I don't know, 2,740 individuals that you counted total. But you notice that they conform to this basic ratio. For every 10 beetles, 4 of them were red. So 4 out of 10 beetles show the recessive. Here they are, 1, 2, 3, 4. Out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total beetles show the recessive phenotype, or red carapace, 4 out of 10. Well, then that might lead you to believe correctly that this q squared is equal to 4 out of 10. The ratio of individuals that have a red carapace is 4 out of every 10. Okay, well, typically this is just me, but I think it's much easier to work with this in a fraction form. So, or not in a fraction form, rather. I would convert this to a decimal form. If you convert this to a decimal form, 4 out of 10 is going to give you 0.4. Now keep in mind, when we deal with these frequencies, there's equations here that I don't want you to get too caught up in. This kind of tells you, this will help you solve some things. P squared plus 2pq plus q squared is equal to 1. Also, P plus Q over here will also always equal 1. This is a probability system here. So, if we know Q squared is equal to 0.4, we need to solve for Q, if we want to get any further. Let's say that I want you to tell me, because we know what these genotypes are, right? I could even label them. I could say little r, right, for this one. Little r. So can you tell me the genotype of all these that have a white carapace? Could you tell me those genotypes? Probably not. And the reason you can't is because there's two genotypes that give rise to this one phenotype, right? All of these white beetles could either be big R or big R little r. So let's say I wanted you to, I told you this population's in Hardy-Weinberg. Let's say I told you that I want to know how many of these white carapaced beetles had this recessive allele here. How many of them are carriers for this trait? Carriers. This is somebody that has the dominant allele but carries that recessive allele. So I want you to tell me approximately how many of these, if our population is in Hardy-Weinberg equilibrium or not evolving, how many of those individuals have this recessive allele? Okay, well, to find that out, we've first got to solve for Q over here. We know Q squared is equal to 4. So all we have to do to solve for Q, as you might guess, is square root both sides. So I'll work that out down here. Q squared is equal to 0.4, right? So of course, you want to get rid of the Q. Get rid of the one of those. That's Q times Q, right? That's what Q squared is. Square root both sides, you should end up with Q. So I'll pull out my calculator here. Okay, now let's do 0.4, and I'm going to square root that. What do I get? 0.632 for blah, 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 blah. We'll round this to 0.63. We'll round that to 0.63. Okay, so Q is equal to 0.63. Okay, so let's go over here. Let's go ahead and fill this out for Q. 0.63. Well, once you have Q, can't you solve for P? Don't P plus Q equal 1? Well, sure. If P plus Q equals 1, then you can subtract P from both sides, right? Or actually, sorry. Since Q is what we know in this scenario. You subtract Q from both sides, right? You can get P. P is equal to 1 minus Q, right? So all you have to do is take 1 and subtract it from, or subtract Q from 1, rather. Let me pull the calculator over here again. Let's just clear this out. 1 minus 0.63 is going to give you 0.37. Okay, so P is going to equal, sorry about that, 0.37. Okay, well, now that you have those frequencies, you can solve for P squared, right? It would be 0.37 squared. So let's take 0.37. And we will just square it. 0.1369. Okay. 0.1. We'll round it to 0.137. How about that? All right. Now we can find 2 times P times Q. Right? So 2 times, and be careful here, you want to look at P and Q over here on the left, times 0.37. Times 0.63. Okay, that's going to give us 0.4662, right? 0.466. Okay, so if you wanted to, you could add all this up and you could find out that it does probably equal somewhat close to 1. It's actually a good way to check yourself. Let's try this. 0.137 plus 0.466 plus 0.4 should give us somewhere close to 1. And it does, 1.003. Of course, we rounded. If we hadn't rounded so much, we probably would get a little bit closer. But that's close enough to 1. So we know that our math here is probably correct. So what does this mean? What this means is, if you will, and remember my original question was, we want to know how many are carriers. Well, I can tell you the percentage that would be carriers in a non-evolving population. That would be 46.6%, or a frequency of 0.466, however you want to look at it. Now, let's say we had a population. Remember, originally I said we had a population of 2,740. All I would have to do is take this 0.466, multiply it by my total population size, and that would give me the number of beetles that I would expect to be heterozygous if this population is not evolving. Okay, let me pull my calculator over and we'll solve this one. 0.466 times 2740, right? So we would expect around 1,277 of these beetles. 1,277 out of 2,740 to be heterozygous, right? Heterozygous, or almost 50%, 46.6. So around half. So if we were to look at our little 10 bug rock over here, we would expect about 3 of these, if I was, rounding a little bit, to be big R, little r, right? That's approximately what we would expect. And of course, the rest of them we would expect to be homozygous dominant. Okay, that wraps this one up. I will see you in the next video.